Good afternoon, my microbiology students, and welcome back. Today we're going to be covering Chapter 12, which describes our host defenses, or at least part of it, which will be the overview of the innate defenses. So some of you may have taken A&P and know that there is a whole separate arm to our host defenses, but my biology students, if y'all taken my class, then you may not quite be aware of that. So don't worry, we're going to go over it, but overall we're going to be describing the innate defense system for this chapter. Chapter 13 will be the adaptive system. So if we look at our outline for today, we're going to first describe 12.1, which is the defense mechanisms of the host. It will be an overview, the big idea, and then we'll go into the first and second lines of defense in parts 12.2 and 3. So it's beginning with the beginning, of course. We'll describe first the defense mechanisms of the host. And essentially, when we are talking about our defense mechanisms, we're describing our immune system. Right, so our immune system is responsible for protecting our body from harmful invaders, and that includes pathogens. As we've described before, pathogens are microorganisms that can make us sick. So our immune system is not just this one thing or this one item. It's a multi-level network of these protective barriers that have one goal in mind, and that's to prevent the invasion of pathogens and to destroy any kind of pathogens that our body detects. So as we stated at the very beginning of this, there are two main branches of the immune system. We have the innate and the adaptive immune system. The innate immune system is going to prevent pathogens from entering our body or spreading, and this is important, in a non-specific way. Meaning our innate immune system protects us from multiple pathogens, not just individual ones. It does not recognize a pathogenic E. coli bacteria as a pathogenic E. coli bacteria. That kind of defense will be described in our adaptive immune system, which is specific. So that's one key difference here regarding the innate and the adaptive immune branches. So again, innate, think natural. Like it is not, it has natural barriers and chemicals that are going to prevent any and all microorganisms from entering or spreading the body, which is not dependent on what the specific microbe is. For example, the skin, our entire skin is a barrier of protection that prevents any and all microorganisms from getting into our body. Other things can include chemical barriers, such as stomach acid. Many microbes are not able to survive stomach acid. So even when we consume various different pathogens, and just incidentally, these pathogens may be too sensitive for the stomach acidity level and die. It's again not selective to certain microbes. Same thing with saliva and mucosal secretions, tears, etc. All of these will have various physical or chemical protective mechanisms that are non-specific. And again, innate, non-specific. The adaptive immune system, on the other hand, is something we'll talk about in our next chapter, which is specific. And what that means is that when we come in contact with a microorganism, utilizing our adaptive branch of the immune system, it's going to involve antibodies and lymphocytes that are going to target specific bacteria or other microorganisms and destroy them. So this week, again, we're going to focus on our innate immune system. So now also, like we said, we describe our immune system as this multi-level framework. So because we have a multi-level, quote unquote, multi-level, it's oftentimes described as in terms of lines of defense, kind of like a battle would be described. And it kind of like is what that is in our body. It's a battle to maintain a safe level of microorganisms and to prevent pathogenic microorganisms from entering and spreading. So just like a battle is being waged, we have our lines of defense in our immune system, and they're described as the first, second, and third line of defense. The first line of defense is any barrier that blocks invasion at a portal of entry. And so portals of entry is something we described in our last chapter. It's any way that the microorganism can invade the host, whether it be through the respiratory system as breathing it in, or consuming it, swallowing it, ingestion, injection, etc. Any barrier that blocks the pathogen from entering a portal of entry to begin with. All of these different barriers that are included in the first line of defense are going to limit access to the internal tissues of the body. For example, most obvious example at least is the skin, like we've already talked about. And again, it's very general in action. It's not specific whatsoever. The second line of defense, on the other hand, is an internalized system, and it's going to include cells and fluids that have protective mechanisms. And it's also going to include inflammatory properties. Inflammation, believe it or not, has a beneficial mechanism behind it. And phagocytosis, another word that I believe we have described before and will again in this chapter. So these are phagocytic cells that are going to be part of our line of defense, second line of defense specifically. And again, in case I haven't mentioned this before, phagocytosis, or phagocytic cells, are cells that eat things. They consume them. They absorb them by surrounding them with their plasma membrane and bringing them inside of the cell itself. So both of these are obviously pretty rapid, especially the first line because it's the initial protective mechanism. But our second line of defense is going to act pretty rapidly as well at both the local and systemic levels. So just to be clear on what we mean by that, local means the site where the entry of the microorganism is. Say, for example, you step on a rusty nail. That site where you stepped on that rusty nail, that hole that is now in your foot, is going to be infiltrated, of course, with any kind of bacteria or other microbes that entered into the skin. So that's a local part of this. Now, systemic levels include other things that are going to happen in other parts of the body, the rest of the body, to aid in the detection, destruction of bacteria, and healing of this site of damage. So these two defenses are what we're going to focus on today. And they are both innate, part of the innate immune response. The third line of defense is the last line of defense. It is part of the adaptive branch. We're going to talk about that next week, but it is considered an acquired immunity that's based on what we've been in contact with. So every time our body comes in contact with some kind of foreign substance, which could be a pathogen, that could be a bacteria or a virus, etc., it's going to be encountered by some kind of white blood cell, such as a lymphocyte. We'll get into more details on what exactly those are in a few minutes. And there will be some kind of reaction that's going to be specific to each microbe that's going to provide a protective mechanism for it. And this provides long-term immunity because it's going to cause the production of antibodies. And we'll get to all that in more detail later, but this may help you. Okay. Bodies. Okay, let me try that again. Adaptive antibodies. There we go. You can't really see my eye. But just the fact that those both start with A, it might help you to remember that the adaptive branch of immunity is the one that involves antibodies. Okay, so, but again, that part's for a later date. Today, what we're going to be describing is our innate immune responses, which includes our first and second lines of defense. Now, we could argue, or is there some overlap? Yeah, there is a little bit of overlap, but let's save that for another day. So, in our innate immune system, we said we can subdivide it into our first and second lines of defense. Again, the first line of defense is any kind of anatomical or physiological barrier preventing a microbe from penetrating. So, this includes physical barriers. I'll give you one example for now: the skin. The microbiota barrier, which is our normal flora. And I know that doesn't look very pretty, but I'm doing my best, flora. But that means basically the normal concentration and kinds of bacteria that are in our bodies, such as our gut, prevents pathogens from being able to take over because they compete with them. And we also have chemical barriers. So one example could be, let's see, amylase is an enzyme that is in certain secretions. We'll talk about that momentarily, but it can aid in the process of destroying microorganisms. And again, this is all innate. It's non-specific to any particular pathogen. Our second line of defense is where we're going to have cellular and chemical systems involved. So for example, phagocytosis. This is a cellular component because phagocytosis is performed by cells, and specifically white blood cells. And we'll go into more details momentarily. Inflammation and fever, as a matter of fact, are both chemical processes. There's a chemical chain of events that occurs that results in inflammation and fever. And lastly, we have antimicrobial products that also play a role as chemicals in this second line of defense. The rest of this over here, we're going to again leave that for another day. All right, so now let's talk about the immune system in general. What's its job? The job of the immune system is three things: surveillance of the body, recognition of foreign material. Now, saying it like foreign material might sound kind of funny at first, but a pathogen is a foreign material to the body. It's something that our immune system does not recognize as belonging with us. So one of the jobs of our immune system cells is to recognize the difference between self and non-self. So if my immune system cells were to analyze my some cells that are in my heart, it would recognize those as self cells and no reaction would happen. But if it encountered some kind of microbe that is not normal, that is a pathogen, then it would have an immune response in order to protect myself from that pathogen growing, dividing, and spreading, etc. So that's where that meaning of foreign material comes into play. It's the recognition of non-self, something that doesn't belong in us. And a side note is that many of our autoimmune disorders, which are, if you can kind of guess, autoimmune, are disorders of the immune system, are a result of our immune system mistakenly attacking things that it shouldn't. So, in that sense, then it's attacking our own bodies and tissues. One example I can think of off the top of my head would be multiple sclerosis. It is a autoimmune disorder that is going to result in antibody production and ultimately attacking of the nervous system, specifically the peripheral nervous system for you AMP people. So that's what recognition means when we talk about recognizing foreign material, self versus non-self. We recognize, or we should recognize, non-self and destroy. And then number 3, our final job of the immune system is that destruction of any entities that are deemed as invaders. All right, so how does our immune system know, though? How does it know which cells are self cells and which cells are non-self cells? Which one are the invaders? Well, of course, our immune system cells, they don't have little eyeballs like we do and can recognize a bacteria versus a eukaryotic cell like we can under the microscope. Instead, they have to do this in a really cool way where they sort of kind of feel the antigens and markers on the plasma membranes of these cells that they're analyzing. So let's backtrack for a moment. Let's talk about what those terms mean. Antigens are markers. We can use those terms synonymously most of the time, but antigens or markers, they are a protein complex or a protein sugar complex that's embedded into the cell membrane, or also sometimes, especially with protein complexes, maybe on viruses, etc. But what happens is our white blood cells, our immune system cells, which are shown here in purple, are going to feel around the surface of these cells. All right, so we can see 4 cells here, and you can see that these blue things are representing various proteins or protein sugar complexes that are embedded into the plasma membrane. Very much enlarged, but nonetheless. And so this white blood cell is feeling those protein/protein sugar complexes, which we call antigens or markers, and determining, is this self or non-self? And as you can see, if it's self, contact with self, and he feels self markers, there's no reaction and this white blood cell moves on. Now, on the contrary, if this same little white blood cell came in contact with a foreign cell, such as this bacteria right here, it also will have little protein complexes or sugar protein complexes on its cell membrane. But in this scenario, when our white blood cell goes to feel around on those little protein sugar/protein only complexes, it's going to say, well, this doesn't look like self. This looks like something I've never seen before. It is not ours, and it will make the choice to then consume it. All right, and then I want you to momentarily ignore these 2 terms. We're about to talk about them. I just wanted y'all to see the process before we start putting all the complex names to it. But again, we are going to have receptors on these white blood cells that are going to feel around for the proteins or markers on the cells in the surrounding area, and if it recognizes something of non-self, it will consume it. And again, this is called phagocytosis or cell eating. As you can see here, that's going to cause destruction. You can see it literally looks like it ate it up, and it did, and it's going to cause that cell to be destroyed. Okay, so now, like I said, we're going to talk about those fancy terms. So the fancy terms were the PAMPs and the PRRs. So the PAMPs, or PAMPs, are pathogen-associated molecular patterns, and that's a fancy way of saying that it's a combination of antigens or markers that lots of different microbes have in common. So our white blood cells recognize these utilizing the receptors that we call pattern recognition receptors. So that kind of makes sense, I hope. So we have our PAMP on a bacteria. So if this is my bacterial cell, and remember it has protein complexes and such embedded throughout its plasma membrane, and here's one of them. And let's pretend that this is looks like this one because I can't draw. But this particular PAMP on this bacteria would be recognized by these receptor sites that are found on the white blood cell. All right, so this is our white blood cell, and you can see it has these receptor sites. They are receiving this chemical signal called the PAMP, which is the marker that is found on pathogens. Alright, so these white blood cells that have these recognition receptors will recognize the pathogen-associated molecular patterns and consume those cells and destroy them. And a side note here, any kind of non-self proteins that are not harmful, because I know some of you may be thinking, well, what about the normal flora of our body? We naturally have E. coli in our gut and a wide variety of other bacteria throughout. What about that stuff? Why doesn't our white blood cells destroy that? And the reason is because it recognizes the particles or the proteins or the antigens, whatever term you want to use. It recognizes them, but it also recognizes that they're not harmful. And so in that case, it generally is just going to be signaled in some way, shape, or form not to react to that foreign cell or to react differently in such a way that it doesn't destroy it. So that helps our immune system to target pathogenic bacteria or other microbes. All right, so all in all, our immune system, like we said, is a network. It's a really great system that does not exist in a single well-defined state. It's large, it's complex, it's multi-level. It has diffuse networks of cells and fluids that permeate throughout every organ and every tissue of the body. So again, it's not just a localized item. It's not just, I know if you think immune system, you might think of lymph nodes, which is a great thing, but our lymphatic system and our immune system is not localized to just lymph nodes. There's all kinds of different organs and secondary organs and tissues that are going to be involved in this process to make it a huge network and complex of surveillance. So what I've put here, is not just one camera, but a whole bunch looking in all different directions. And so the surveillance mechanism that our body has is going to help screen the body throughout, not just locally, but systemically, system-wide, for any kind of harmful substances. All right, so let's talk about the tissues, organs, and cells that are going to participate in this immunity. So for effective immunity responses, we need to have our compartments of our immune system communicating with one another. So again, remember we said this is not a localized event, it is systemic wide. Now there are sections in the body that we call our mononuclear phagocyte systems that do have higher concentrations of our phagocytic cells. And again, those are our cell-eating cells. But these cells are also not necessarily stationary. They come in direct contact with tissue cells and the ECF, and that's the extracellular fluid, which is all the fluid that's in between cells. So if you look at our bodies, let's say any part of the body, it really doesn't matter, but if we have some cells here, there's space in between those cells. And there's fluid in between those cells. And that's what we mean by the ECF, is all the space which contains fluid in between cells. So these immune system cells are in direct contact with not just the cells and tissues, but also that extracellular fluid that's in between cells, and they can flow in this way in order to reach different parts of the body. Also, blood and lymphatic capillaries penetrate into all tissues throughout the body too. And I know if you took A&P, you know what I'm talking about. If you took biology, give me just a second. We're going to come to that with some pictures so I can show you what that means. But this infiltration of these different systems coming together, the lymphatic capillaries, the blood vessels, and the phagocytes that are infiltrated throughout, are going to allow them to be able to access these blood capillary or lymphatic capillary vessels, and that way it serves as a highway to other parts of the body. Again, that means we can reach system-wide. All right, so like I said, for you bio people, I know A&P people probably already know this, but I want to review it just because I feel like it's necessary for this specific topic. But what this is showing you in these two images here are the cardiovascular and the lymphatic systems. So our cardiovascular system is also called the circulatory system. But we see it has the heart, and it has all of these arteries and veins that are dispersed throughout, and essentially they're branching and branching and branching into smaller and smaller and smaller arteries, and smaller ones and smaller ones and smaller ones, until eventually we call them arterioles, and then eventually those lead into little tiny blood vessels called capillary beds. And at those capillary beds, we see, let's see, how am I going to explain this without getting too deep into A&P? I'll leave it at this. The capillary bed's major function is they're a site of oxygen exchange and carbon dioxide. So, but they're going to be continued by veins. So arteries will end in capillary beds. We have oxygen and carbon dioxide exchange, and then a continuation of those arteries will be veins that will unbranch and unbranch and unbranch and unbranch and lead back to the heart eventually. The lymphatic system's kind of similar in that way because it has lots of different vessels. We won't go into the details of it for our class's purposes, but what you can see here is some similar pathways as we see in the cardiovascular system, where we see lots of branching, creating vessels throughout the body, where these are called blood vessels, these are called lymphatic vessels. So we're going to come back to that. The phagocytes that we were talking about, we said that they can infiltrate this tissue, these lymphatic vessels and these cardiovascular vessels. But where are they primarily found? They're primarily found in certain sites of the body, but it's still pretty widespread. So for example, they're found in the thymus. This is actually one of the sites of white blood cell maturation. And that's going to be around here. Lymph nodes, you see all these little purple highlighted areas. Many of those areas, including up here around the neck, the groin, etc., all scattered throughout, we have lymph nodes. The tonsils are going to be more specific to the facial area, and the spleen, of course, in our abdominal cavity. Additionally, we have some lymphoid tissue of the mucosa of the gut and the respiratory tract. So respiratory tract here, and also in the gut we have various patches essentially of lymphatic tissue that is responsible for assisting in the concentration of these phagocytes. So our phagocytes are loaded with these white blood cells that we call macrophages. That's a new word, all right? So a macrophage is a type of phagocyte. So macrophages are cell eaters, but they await in these areas of concentration of these various areas like the thymus and the lymph nodes, tonsils, spleen, etc. And they wait for any kind of foreign intruders to enter the body. And when they do, they arrive at these locations, attack and consume and destroy said pathogen. All right, so let's talk about, now that we've looked at the anatomy of our cardiovascular and lymphatic system, at least in a very, very, very brief sense, let's look a little bit more at our functions of our lymphatic system. So again, what you're seeing in this picture is lots of branching patterns. This branching pattern provides a route for the return of extracellular fluid to the circulatory system. So our circulatory system and the lymphatic system are very, very closely intertwined. But the lymphatic system almost acts as like a drain-off system for any kind of inflammatory response or excess fluid in the body. But it also is going to aid in surveillance, recognition, and protection against any kind of foreign materials. And it's going to do so through the process of white blood cells like our lymphocytes or phagocytes such as the macrophages and antibodies. Now the phagocytes are what we're talking about this chapter because this is the one that is going to be considered our innate immune response. We'll talk about these other two next week. So recall that I said that the lymphatic system infiltrates into tissues along with the cardiovascular system. This is a picture of that. So I don't know if I'm going to be able to draw this, but here I have a human head. Here's the neck. and arm. Don't judge me. Okay, so I have my heart right here, okay? And so we said earlier that our heart is going to have extensions of it called blood vessels, specifically arteries, that are going to take blood to various places in the body, and it's going to branch and 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 branch into eventually we get very tiny blood vessels called capillaries. Okay, so that's what this is here in these red and blue vessels. All right, so here we see the arteriole end, and remember I said they're continuous with veins after the capillary bed. So we have the arteriole. Honestly, I wish this picture would be upside down because it would make more sense with the way I drew my drawing here, but really it doesn't matter. But we have the arteriole end, which is where the arteries, the small arteries, they're smaller ones. Remember I said they branch and get smaller. And there's certain rules, we're not going to worry about those. That's an A&P thing about how you describe them. What's the diameter got to be for it to be an arteriole? For my class, for this class, micro, I don't care. But this is the arteriole end, and it branches into these tiny little blood vessels called capillaries. And these little tiny capillary beds are very, very tiny. In fact, they're so small in diameter that like one red blood cell can fit through there at a time. So pretty itty bitty. So additionally, they're made up of tissue that is very permeable. And for you A&P people, you might remember that it's made up of simple squamous epithelial cells. I don't care if you know that for micro, but for my purposes, my point is that that type of tissue is very permeable. So we're going to have fluid that will be exchanged between the extracellular matrix, or the extracellular fluid, whatever you want to call it, and the inside of these capillary beds. Here on this end we have the venule side, which is the site of return. This will eventually flow back to the heart, going the opposite direction, all the way back. But at these capillary beds, we also see this green stuff. These green things are lymphatic vessels. And so what occurs is we have a very high pressure relative to the pressure on this side of our system, very high blood pressure. And so the blood is going to flow through these capillary beds. The red cells will stay within the walls of the blood vessels, but we will have fluids seep out into the extracellular fluid. Some of this fluid is going to be trapped inside of these green lymphatic vessels. And there it will travel throughout the lymphatic vessels, throughout lymph nodes, throughout other immune system organs or lymphatic organs that are going to aid in the detection of any kind of pathogens that existed in the blood. So this is how our immune system detects these pathogens systemically, like in the blood, which is dispersed throughout our body. All right, so let's look at our lymphatic organs. The primary ones are the sites of where we have immune cells being quote unquote born and maturing. And that includes the thymus, which we mentioned earlier, as well as red bone marrow, which is located inside bones. Specifically towards the ends of long bones usually, but again that's kind of one of those things I wouldn't expect you to know the specifics of for micro. So the secondary lymphatic organs include things like lymph nodes. That's all these little balls of green that you see throughout this picture. The spleen, located here, as well as associated lymphoid tissues. This picture does not show the associated lymphoid tissues very well, or at all really, because it does not show the organs that would have those. So we'll look at that again at another time. So looking back at our red bone marrow, we said that this is going to be typically found in the ends of long bones, also technically in flat bones for you A&P people. So if we look at the inside of this long bone, this is a femur bone, we can see that we have some red stuff here. This is the red bone marrow, and this is the site of blood cell production. And B lymphocytes mature in the bone marrow. After they mature, they're going to move and settle into the lymph nodes and the spleen. All right, so B lymphocytes, I'm just write B cells. They start in the bone marrow, specifically red, and then they mature and travel to the lymph nodes and the spleen. So if I was a student and I was trying to remember that pathway, this is how I would have written it out, to try to abbreviate everything so it would be easy for me to remember. Now, the thymus, on the other hand, we said that's the other site of maturation of various lymphatic cells. So those are the T cells, which is kind of nice because guess what? T cells, thymus starts with T, so that's nice. The T cells originate, though, in the bone marrow still. They all originate in the bone marrow, but the T cells, they are going to migrate to the thymus for maturation. So that's a little, kind of make sure you know the difference there. We have, again, blood cells, T cells, T and B, originate in the bone marrow, but T matures in the thymus, and B matures in the bone marrow. So they're they're originating in the bone marrow. The difference is where they mature at. T cells, thymus. B cells, bone marrow. All right, so then afterwards, these T cells will then navigate to, once again, the lymph nodes or the spleen. Do they stay there forever? No, but that's their next spot of interest. Speaking of the lymph nodes, let's talk about those next. These lymph nodes look kind of like beans inside of our pictures that we've seen so far. And what they are, they're little tiny encapsulated organs that are typically going to be found in clusters. And they'll be found in clusters along our lymphatic vessels throughout our body. And aggregations of lymph nodes can be found in specific areas of the body, but they're also widely dispersed throughout, but they do have larger aggregations in certain areas like the neck, the groin, and the armpit. And so then it's no surprise then that when you go to the doctor and they are doing like an annual physical, they're going to feel around on your neck because they're trying to indicate or feel or palpate your lymph nodes to see if there's any enlargement, because that can provide them with important clues to a patient's condition. They probably don't feel the ones in the groin because that would get weird. And the armpit, they're not as palpable due to you typically have more fatty tissue there than you do in your neck. And they're more superficial in the neck. Alright, so the spleen is our next organ of interest. We've seen where it's located over here next to the stomach. So it's found in our upper left-hand portion of the abdominal cavity. And before I move on, I want to make sure that we are clear on why this is upper left. Alright, so I know you A&P people know why. And it's because we need to think of this in perspective of anatomical position. Bio people may not be familiar with that, but essentially when we are describing directions left, right of the body, we need to think of it in the patient's perspective. So while I'm looking at this and it's on the right to me, it is the patient's left side. Alright, so I just wanted to be clear on why it says upper left portion for those of you who are not familiar with anatomical position. So this is a site, an organ that is responsible for filtering blood rather than lymph, and it's going to remove worn out blood cells. Blood cells don't live very long, especially, well, let me backtrack that and say red blood cells, because they actually don't have a nucleus, which is kind of unique. And so because of that, they're not able to repair themselves or make new proteins, so they are going to wind up dying within about 3 months or so. So at that point, they'll be sequestered by the spleen and broken down, and their components will be recycled as possible, and if not, everything else is excreted. But also, the spleen will filter out pathogens in the blood, and it will assist then in that phagocytic process by macrophages, cell eating. All right, our associated lymphoid tissues. These are the things that I said wasn't in that picture very clear, so I believe I have it in an upcoming picture. Oh, I thought I did, but I didn't. That's okay. But basically, it's you can't really it's not an organ. See, it's not something you can really like have a picture of per se, I guess. But all it is this discrete bundle of lymphocytes, like patches of them, literally, at various sites throughout our body. And so these can be in various areas. It can be in the skin, and whenever they're in the skin, it's called the SALT, which stands for skin-associated lymphoid tissues. Makes sense, hopefully. The MALT, mucosa-associated lymphoid tissues. The GALT, gut-associated lymphoid tissues. Things like the appendix would be considered part of the GALT. The lacteals of the intestinal villi, which are associated with our immune system, are part of the GALT. Peyer's patches. These are literally aggregations of lymphocytes in the ileum of the small intestine. All right, and so the ileum is just a section of the small intestine for you non-A&P people. I don't expect you to know like the order of the various parts of the small intestine or anything like that. Just know the things that are that I'm indicating are for our purposes. Peyer's patches are located throughout the small intestines, and it has an immune system purpose. Oh, and I forgot the tonsils. Those are located, of course, inside of our head, particularly near the pharynx or the larynx. For those y'all non-A&P people, that's going to be part of our respiratory tract and the various sinuses in our head. And we'll leave it at that. All right, so let's move next to the blood. What is blood? Whole blood consists of cells and plasma. The cells that are in blood are oftentimes called blood cells, and we refer to them as the formed elements. Why are they called the formed elements? I guess because they're solid particles, I suppose. I don't really know the answer to that. That's just always what I assumed, but I thought it was weird when I heard the word formed elements for the first time in my life, and that's how I've always thought about it. But these formed elements, these solid particulates, i.e. cells, are suspended in plasma, which is a clear yellowish fluid. So I know we've probably all had blood drawn before. If you've ever had your blood drawn, again, I feel like most of us probably have, you're going to notice that they draw it in these tubes. And these collection tubes, when they are filled with blood, we're going to have a tube of red stuff. Okay? So now, what happens behind the scenes in a clinical setting is this tube of blood is going to be put into a machine called a centrifuge. And essentially I relate a centrifuge to kind of like the gravitron at the fair. So I don't know, I bet most of you have probably been to the fair and know what I'm talking about. It's that little spaceship looking, then it might have a different name now, what do I know, but it's a spaceship looking quote unquote ride, and you get in it and it spins really fast. And so what happens is that causes you to be pushed up and against the walls of that ride. And so in a similar way, the centrifuge is going to force particulates by weight or density into various areas of the tube in such a way where the heavier stuff is at the bottom. Heavier stuff to the bottom. And of course, then that means the lighter stuff is on the top. So if we look at this here, this is what our blood would look like after it's been centrifuged in a blood collection tube. So we'll see the heavier stuff, which is the erythrocytes. Those are the red blood cells. Why are they so heavy? Iron. They have iron in them. It's part of our hemoglobin. We have the buffy coat. This includes our platelets and the leukocytes. Leukocytes are white blood cells. And then at the top, we have plasma. The plasma is mostly water, and it also contains light proteins like albumin, electrolytes, which are various ions, and gases such as carbon dioxide and oxygen. So, one thing I wanted to point out that I think will be relevant to you at another time, I'm not going to ask you this on an exam, but I do think it's important for y'all to know this for a later date, like your nursing classes, is the difference between plasma and serum. So you may have heard both of these terms, and if you haven't heard them yet, I would bet money that you will hear them at a later date in your nursing classes. But what's the difference? Because a lot of people assume they're the same thing, and they're not. Not quite. Almost. The difference is that the serum is plasma minus the any of the sorry, I had to pause it because I just spilled my drink, you guys. My bad. Let me get back to what I was saying. So we were just talking about the difference between plasma and serum. So plasma is that liquid portion of blood that we see here in our collection tube. Serum, on the other hand, is almost the same. The difference is, in this case, we don't have an anticoagulant in the collection tube, so blood is allowed to clot. And so there won't be any clotting factors in serum, while there will be in plasma. So anyway, that's really just a side note for future reference. Impress your nursing teacher, maybe. But anyway, moving on to our next point. Where do these cells come from? We said the bone marrow, which is correct. But what's the process called? It's called hematopoiesis. And again, this might help you in remembering. When you think hema, think blood. When you see poiesis, think production of something. So production of blood cells. That includes the white blood cells, the red blood cells, white blood cells, and platelets. They derive from stem cells. These are precursor cells that are going to be responsible for proliferating new cells that will then differentiate into specialized forms and functions. They can become, again, red cells, white cells, or platelets. Our white blood cells are the ones that are involved in the immune system. They are also called leukocytes, and they can be subdivided into granulocytes and agranulocytes. And the reason why they're called these things, granulocytes look granular under a microscope. They look like they have grains of stuff in them. And guess what? Agranulocytes don't. They don't look granular. And so that's how they're subdivided into granular versus agranular cells. And these cells are very important to our nonspecific immunity as well as specific immunity that we'll talk about next week. So in summary, we're not going to go through all the different steps of hematopoiesis in this class, but again, what it is where we have a stem cell that we call a hematopoietic stem cell. And again, it's going to be found in the bone marrow, specifically the red marrow, and it will make more cells. It'll undergo mitosis, and regardless if you've been in A&P or biology, you should know that word, where it makes more cells. Those cells can differentiate to become certain types of cells. And this chart here displays all of the different types of cells that a hemopoietic stem cell progeny can become. So we have our agranulocytes, we have our granulocytes, both of which are considered leukocytes, which are the ones we're interested in this chapter. And then our non-leukocytes, we don't really care about those this chapter. That's our red cells and platelets. But again, the leukocytes are the white blood cells. So let's look at this variety of stuff here and see what we might have discussed so far. Have we talked about monocytes and dendritic cells yet? No, not really. We have talked about macrophages. We said that they are phagocytes. We've talked about T cells and B cells. These are two different varieties of lymphocytes that are part of the adaptive immune response. So we're going to leave out any further details on those for next week. We have some NK cells, which are called natural killer cells, and we have these two cells here, which is going to relate to that part of our excuse me, chart that we saw in the beginning that kind of overlaps. Let's look to excuse me, our granulocytes. We have our neutrophils, basophils, eosinophils, and mast cells. Excuse me, sorry. I got something in my throat. But anyway, so these are all the different varieties that can arise from these hematopoietic stem cells that are found in the bone marrow. So let's talk about some other examples of components of the immune system that are important. So we've talked about the various cells. We'll get more detail on those later. But now let's talk about some chemicals. Cytokines are one example of a chemical that is found as part of our innate immune response. These are little molecules that are secreted that help to stimulate, suppress, or regulate a lot of different components of our immune system, as well as cell development, inflammation. You can think of them as a regulatory mechanism. But these different chemicals are produced by cells such as monocytes, which are a form of macrophage, also macrophages, lymphocytes, fibroblasts, mast cells, platelets, and endothelial cells. Endothelial cells are cells that line a surface of the body, whether it be inside or out. So before we move on, I do want to, because we talked about both monocytes and macrophages now, and you might be thinking, well, I don't get it. What's the difference? Monocytes are in the blood. When they leave the blood, remember we said these cells don't stay stationary. They're going to travel to a site of infection. When they do so, they're going to be converted into macrophages or dendritic cells. And the difference is basically where they're traveling to and what their job is going to be there. All right, so now here's a list of various cytokines. Note here, I do not expect you to know these. I'm just showing you examples and what they do. What I would want you to know is cytokines include hundreds of molecules that regulate the immune system. Does different things depending on each cytokine that we list. And I don't expect you to know all these specific examples. But for example, if we look at examples of pro-inflammatory cytokines, those encourage the immune response. Inflammation is part of our immune response. We have interleukin 1, tumor necrosis factor beta, which is this one here. Some others, anti-inflammatory cytokines, interleukin 10. Vasodilators and constrictors, those open up or constrict our vessels, our blood vessels. Serotonin, histamine. Growth factors, interleukin 7, erythropoietin, which stimulates the production of new blood cells. So again, I don't expect you to memorize this whatsoever. Just know that the immune system is regulated by cytokines that do various things to control cell development, inflammation, and immunity. So that was 12.1. Let's move to 12.2. Our learning outcomes here are to identify the 3 components of the first line of defense. We'll identify the 4 body systems that participate in this line of defense, and we'll describe 2 examples of how the normal microbiota contribute to the first line of defense. So our first line of defense, a lot of this is going to be a little bit reiterative because we started with the overview, so we're getting to a little more details here. But again, the first line of defense is inborn, meaning we're born with it. It's natural because it's innate. It's non-specific. It's any physical and chemical barrier that prevents microbes from entering the body. So some examples are shown all throughout this image. So we have sebaceous glands. These are glands found in the skin that produce oils. Tears. These are obviously secretions from the eyes, but it contains lysozyme. That's an enzyme that can help destroy microbes in a general sense. The fact that we have earwax can trap bacteria. Same way with mucus. That's, I guess that's kind of why you get boogers, right? So we get particles and stuff that's trapped in the nose and the nasal hairs, and those are ways that our first line of defense prevents microbes from passing into the nasal cavity and going through it down to our respiratory tract. Saliva, again, flushing action, has lysozyme. Something that is found in the airways here is called cilia. I have a picture of that in just a second, so we'll hold that thought. Let me make sure, see how far away it is. There it went. Okay, so we'll come back to that and what it is. But y'all should know what cilia is because we talked about it in biology and y'all should have also talked about it in A&P. But cilia are these little hair-like extensions that can be found on certain cell surfaces. We see stomach acid. We talked about that already as being a physical or chemical barrier to prevent microbes from passing further into the GI tract. There are various intestinal enzymes. There's mucus still within the GI tract. The fact that we urinate and defecate is going to also flush out certain microbes and other organisms that get inside of the body. So these are built-in defenses. Now, let's talk about the skin in a little bit more detail. So for you A&P people, y'all should have have covered all the various layers of the skin, I'm sure. But for us, for our purposes, all I care that you know about is the stratum corneum. And this is a tough outer layer of the skin that's impervious and waterproof. This is the portion of the skin that's constantly sloughing off throughout the day, and it's going to remove any microbes that are on the skin. And as it sloughs off, there's going to be a basal membrane below our skin at the bottom that is going to be making more skin cells. Also, our hair, the shafts of our hair periodically shed. You brush your hair, you're going to have some hairs on your brush, and that's normal. So that's going to allow for the cells in the hair follicle to be desquaminated. That means to shed, essentially. And so again, that allows for our, it prevents buildup, essentially, and prevents microbes from being entrapped in the hair follicles. So this flushing effect of sweat is our next point here in regards to the skin and hair, and that will also assist in the removal of microbes. So we now want to discuss our defenses of mucous membranes. So we said that mucous membranes are pretty widely distributed throughout our internal parts of our body, and that mucus is going to impede attachment of bacteria. So just imagine a little bacterium getting stuck in your snot, for example, and then it gets trapped. So it's because snot is a mucus, it's thick. Blinking and tear production flushes the eye's surface to avoid penetrance of a microbe. Saliva, we're constantly making saliva, and that is going to allow the microbes to be swallowed, where they're going to then come in contact with the stomach, and as y'all know, it's very acidic in there and many bacteria just can't survive it. Vomiting, throwing up, defecation are also a way that we can evacuate any kind of substance or microorganism that our body is not okay with. So substances meaning anything, toxins, for example, that microorganisms can produce, as well as the microorganisms themselves. Hence why if you ate something raunchy that might have been left out a little bit too long, you're probably going to have some GI symptoms, which include potentially vomiting and diarrhea. Fun stuff. Let's go on to that respiratory tract. How is it going to serve as our first line of defense? Well, we have hair in our nose. Those little hairs in your nose are going to trap particles within them to prevent them from continuously flowing towards the back of the respiratory tract and ultimately to the lungs. We also have plenty of mucus production, and y'all would know that especially if you have children, because they are some snotty creatures. But again, that provides a flushing action. The cilia of the inner linings of the respiratory tract are going to also help trap particles like bacteria. So what we're seeing here, this is the windpipe. If we look on the inside of that, here would be the lining of it. These are the epithelial cells. And here we see all these little hair-like extensions. These are the cilia. And what we're seeing here is a bacterium that is entrapped, and we see another one too. Now, as we talk or breathe or sneeze or cough, etc., the cilia are going to push up these particles that it's trapped. Think of it like an escalator, a cilial escalator. This is an eye. All right, a celial escalator. It's taking those particles that is trapped and it's moving it up as we sneeze, cough, talk, etc., and expels them out of the respiratory lining. So maybe you hack something up. I know that's really gross, but mucus from the respiratory tract, and then you swallow it. Well, now it's going to your stomach, which again, we've said most bacteria and microbes cannot withstand that pH. Sometimes you may sneeze it out. Sometimes you'll hack it up and cough it out and throw it in the trash, which is preferable in my opinion, but hey, you do what you do. But that's going to allow for us to remove any kind of bacteria or mucus from getting into the lungs, because that's just becomes a place where we really don't want pathogens and fluid to enter. Now, next, our GI tract. It provides protection through the continuous trickle of fluid, i.e. urine, and then of course we urinate after our bladder is full, and it flushes the urethra, which is the tube that the fluid will come out of. So just for reference, I'll draw this very briefly for my non-A&P people, but again, I don't really ask very many A&P specific questions on my exams because I understand not all of y'all have taken it. Here's my kidneys, poorly drawn, naturally, because I'm a terrible drawer. But extending from the kidneys, we have these little tubes. There we go. So these, again, kidneys, are going to filter fluid from the blood, and then it's going to take the excess fluid to the ureters, which are these two things. So the flow is going down, 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 down. And now we have our bladder. This is where urine is stored. And eventually, once we feel the urge, we will urinate through our structure here called the urethra. And I couldn't quite finish my lettering there. So I'm going to draw it again. Urethra. Alright, and that will allow that urine to be expelled from the body. So again, ultimately we have this constant moving of a fluid that is going to flush out any kind of bacteria that would be in our urinary tract. Hence why if you ever have a urinary tract infection, the first thing they're going to tell you to do is drink a ton of water to help flush those bacteria out. Additionally, our vaginal secretions in women provide a cleansing mechanism of the lower reproductive tract for females. Again, another example of a acidic environment that will have specific enzymes that are capable of destroying microbes. Alright, next, our human microbiome. We said this was another mechanism that serves as a barrier for microbial infection. And so our microbiome is our normal flora. It's the normal bacteria that we have in and on our bodies. And those normal bacteria that are existing are going to compete with other bacteria that come into or are on the body that are considered pathogens. So typically that microbiome is pretty a great thing. It's important because it will ensure that it's an unfavorable environment for pathogens, because they're competing with limited nutrients. Sometimes they'll alter the pH, which will deter pathogenic bacteria from wanting to be in the same area. But that might brings us to this next point, though. So when we get sick, let's say it's with a bacteria, what's the first thing that's prescribed to us? An antibiotic. Now, antibiotics, as we've talked about in the past, are not always or rarely, if ever, specific to a single bacteria type. There can be some that are narrower in spectrum, but there's a lot that are broad spectrum, and regardless, again, none of them are ever going to be as specific, at least so far, to individual bacteria. So whenever we consume an antibiotic, it's not going to wipe out just the bacteria we're trying to kill, but also some of the healthy bacteria. So that's why they say one of the common side effects of taking antibiotics can be GI upsetness. And in fact, we now believe it's possible that Crohn's disease and ulcerative colitis, which are both examples of GI tract conditions, may be the result of a disruption in our microbial flora due to the overtreatment of antibiotics, resulting in a gut microbiome that is not that doesn't do the same thing as our natural one that we had from birth would have. Alright, so next let's look at some chemicals that are going to assist us in our innate immune response. Those sebaceous secretions can have an antimicrobial effect. We have glands that are found throughout the eyelids that will lubricate the eye and have also antimicrobial secretions. We mentioned lysozymes already that can be found in tears and saliva. And what it does, now notice this one's bolded because I like it. It means it may be on the test. It hydrolyzes peptidoglycan. What did we say that bacteria's cell walls are made out of? For most bacteria, not all, but a lot of them. Peptidoglycan. What does hydrolyze mean? Hydrolyze, think hydrolysis reactions. For you bio people, not sure if you A&P people talked about it, but what you can think about it as for my class is lysis. Lysis means to break down. So if we have a bacterial cell and the cell wall is made up of peptidoglycan, and it's in my eye, and I have tears in my eye, then that lysozyme enzyme that's in my tears is going to destroy the cell wall of this bacteria and thus kill the bacteria. We said sweat is also a preventative mechanism. Well, why? Because it has a lot of electrolytes, which are various salts, and lactic acids, which will throw off the osmotic balance of our bacteria, causing it to potentially rupture and die. We have a acidic pH and fatty acid content on the skin, which also assist in our innate immune response. The stomach, very acidic. It has hydrochloric acid, making it a very low pH that many bacteria cannot withstand. Our digestive juices and bile in the intestine also have various enzymes that make it more difficult for microbes to survive. Semen even has antimicrobial chemicals within it. And like we've mentioned before, in the vagina it has a protective pH. And there are also various cells and enzymes that exist as the normal biota within the vagina that will assist in this nonspecific defense process. So what happens when we lose one of these barriers? If we have a loss of one of those barriers, it's going to basically weaken our immune system. So a great example of that is one of the most common complications of burn patients is bacterial infections, because they've lost skin. And so now they are susceptible in that area of skin loss of microbes. Blockages in salivary glands, tear ducts, the intestines, and the urinary tract are all going to be indicators of a greater risk of a bacterial infection, because less flushing action in all of these areas, less immune system cells, less enzymes and immune system chemicals that are going to be able to protect the body. So the first line of defense, though, luckily is not the only line of defense, and it alone is not sufficient protection. So we're going to talk about other means of immune response in our upcoming slides. So our last slide that I want to cover for this PowerPoint is just a concept check, something for you to think about, give you an example of a question that you may or may not see on the exam. But it asks for each of the barriers below to state whether it is a physical or chemical barrier. Alright, so our next section is 12.3. I'm going to make this a second video because we've hit just a little over an hour, and I don't like to lecture longer in a video than 1 hour. So I'm going to make this a second video to do 12.3. Alright, you guys, I will be back with you momentarily.